Hello everyone. In the series of learning database management system, today we are going to solve some examples on lossless join decomposition and dependency preserving decomposition. We are going to check whether the given decomposition of a relation is lossy or lossless, whether it's preserving the dependency or it's not preserving the dependency. Here I am taking few example, and I have taken the example from GATE also, so you can take the gist what kind of question you can face in your competitive exam, and what kind of question, how you have to solve them quickly. So prerequisite for this particular lecture is the lecture which I have uploaded earlier, lossless join decomposition and dependency preserving decomposition. If you have not gone through those videos, first check those videos, then only this topic will be understandable. So here we are having a relation R, and in this relation we are having four attributes W, X, Y and Z. The functional dependencies are as follows. We are having W determines X, X determines Y, Y determines Z and Z determines X. When we are decomposing the table to bring it to some normal form and to reduce the redundancy, we are getting three tables, that is R1, R2 and R3. R1 is having two attributes W and X, R2 is having two attributes X and Y, and R3 is having two attributes X and Z. Now we have to check whether it's a lossy decomposition or a lossless decomposition, whether it's a dependency preserving or not dependency preserving. So three properties I have told you to check whether it's a lossy or lossless decomposition. If it is a lossless decomposition, there should be three properties, 3 points to remember I have given in the previous lecture series. If from R1, R2, R3, which are the child table, we can be able to recreate the table R, all the attributes. If I am getting W is present, WX, Y I will get from this table, and Z I will get from R3 table. If I will join the table and I am able to get all the attributes, it can be a lossless join decomposition. After that, second point was that there should be a common attribute between these these three tables. So here if you can see, in these two tables X is common, in these two tables also X is common. So there is a common attribute. So second point also satisfied. Third point was this common attribute must be a key. So here if you can see, in any of the table, okay, means the value of this X should be distinct. So if here you can see, this X will act as a key for this. So in any of the table, if X is key, that's sufficient. If it is a key, it cannot take duplicate value and it cannot be null. So there will be a uniquely identifiable attribute, and on the basis of that we can easily join the table and we will not get any redundant tuples also. So we can say this join is a lossless join. Now what we have to do next, we have to check for dependency preserving. It is dependency preserving or not. So now we already studied in the previous lecture, I have given you 4 points for dependency preserving or not. So let's solve the numerical one by one. So here, first point for dependency preserving, write down all the non-trivial dependency present in the child table. So what we are saying here, these R1, R2, R3, we are saying the child table, and we have to write down all the non-trivial dependency. Why only non-trivial dependency? Because trivial dependency always hold true. If I am saying X determines X, of course X can determine X. There is no point of checking there, right? So we are not going to write the trivial dependency. We are only going to write the non-trivial dependency from child table. Okay. So here I am having three tables. So I am just making a separation like this. Okay. Now here I am having the child table as first child table I am having WX. Second child table I am having XY, and third child table I am having XZ. So this is my R3 table, this is my R2 table, and this is my R1 table. Here in the child table, individually we will write the non-trivial dependency. If I will write non-trivial dependency with respect to R1, W can determine X. There can be a possibility that this non-trivial dependency can be there, and X can determine W. So there are two possibilities which can be true. Similarly, when I do for this, X can determine Y and Y can determine X. Next, for this table, X determines Z and Z determines X. So these are the possibility. I have written all the possible non-trivial dependency which can be present in the child table. Now next, what I have to do, second point, check the dependency hold true or not. Now for this there can be two cases. Dependency can be directly present in the question. So if you can see here, from here we will see W determines X. In the original functional dependency given to me, W determine X is directly present. So without further checking, I can say that this dependency is true. Next, X determines Y. Now X determines Y is not, X determines W. X determines W is directly not present in the table. So we will hold for this. Similarly, we will check for R2 and R3. X determines Y is directly present. Y determines X is directly not present. X determines Z is not present directly. Z determines X is present directly. Okay, so here what we have seen, check the dependency hold true or not. Dependency can be directly present. So this point we have checked. Now if the dependency are not directly present, then what we have to do? If the dependency are not directly present, we have to take the closure. We have to take closure of the determinant. Of the determinant means I am checking for these. X is present, X determines W is present or not. So what is the determinant here? X is the determinant. Okay, so I will take the determinant's closure with respect to the functional dependency given in the question, and then I will check the possibility. Now how I will take the determinant? I will take the determinant with respect to the functional dependency given in the question. Okay, let's check the determinant here. The determinant is X. I am taking the closure of X with respect to the functional dependencies given in the question. So here if you can see, X determines Y, and of course X can determine X. So I am writing X determines X, X determines Y. Now Y determines Z. So I am writing here Y determines Z, and Z determines again X, which is written, but there is no chance that X determines W. We are not, if I am taking closure also, then also I am not getting any chance that X determines W, right? That means this dependency is not true, because we are not getting the closure. In the closure we are not getting, in the closure of X I am not getting W. So this dependency will not hold true. This is a false dependency. Okay, so like this we will separate out. Now similarly what I have to do, I have to take closure of Y for this with respect to the functional dependency given in the question. Now when I will take closure of Y, here Y can determine Y and Y can determine Z. Okay, and then Z can determine X. Okay, so in this table we are only having two attributes, X and Y. So this Z we cannot accommodate here because this is not part of this table. So we can say that if I am taking closure of Y, I am getting Y and I am getting X. And what is the functional dependency? Y determines X. Thus it is not directly true, but indirectly it's true. Fine, Y can determine X. Similarly, now here we have to take closure of X. If I will take closure of X, I will get X, Now with respect to the functional dependency given in the question, here x can determine y and y can determine z. Okay, so here what you can see, z can determine x, but it's already written. Okay, now what you can see here, this table is only containing y and z, sorry, x and z. So y I cannot accommodate here. So I can say the closure of x is x and z. So I can tell that x determines z is also true. Fine, it's not directly given, but it is indirectly given. So right now I got all the possible functional dependency. Now what is the next point? Next point is take union of all possible functional dependency. So I have to take union of all possible functional dependency. So if I will take union of all possible functional dependency, here I am writing possible functional dependency. So what and all I am getting? From here I am getting, W determines x. From here I am getting x determines y. Then I am getting y determines x. Then I am getting x determines z. And then I am getting z determines x. Okay, so the union of all possible functional dependencies is this. This is the functional dependency I have right now. So let's see the fourth point. Now fourth point says check all the original dependencies are preserved and not with respect to the functional dependency, possible functional dependency. Now here also there can be two cases. First case, dependency can be directly present. If dependency is directly present, we will say that dependency is preserved. If it is not directly preserved, again we have to take the closure of the determinant. Now this time we will take the closure of the determinant with respect to the derived possible functional dependency. So let's see here. Now I am checking this and this. That's what we have we were saying, right? That if the functional dependency which is present in the child table is equals to the functional dependency present in the parent table, then the functional dependency is preserved. So now we are comparing here. So first dependency is W determines X. W determines X is directly present. So this dependency is preserved. X determines Y. X determines Y is also directly present. So this dependency is also preserved. Next, Y determines Z. Now Y determines Z is directly not present. Okay, I will check for this later. Here, Z determines X. Z determines X is also directly present. Okay. Now, what I have to do? I have to check for this. Y determines Z. So what I have to do? I have to check the closure of the determinant. Now, I am taking the closure of Y. Y can give me Y. And this time I have to do this with respect to the possible functional dependency. So Y can give me Y. Y can give me X. And X can give me Z. Right? And Z can again give me X. But it's already written. So what is the dependency? Y determines Z, and if you can see, closure of Y is giving me Z. So this dependency is also preserved, right? So here we can say that all the four dependency, W determines X, X determines Y, Y determines Z, and Z determines X are preserved. Fine. So this particular example is a lossless and dependency preserving example. Let's solve another one. Here we are having four attributes A, B, C, D, and we are having the functional dependency A, B determines C, C determines D, and D determines A. And here this is decomposed into two tables. First, let's see, it's a lossy or lossless. So here you can see I'm having A, B, C from first table and D from another table, all 4 attributes I am getting. Then you can see C is common, and here if you can see C is the key. Fine. So it is a lossless decomposition. After that I have to check whether dependency is preserved or not. So here I am having the table A, B, C, and here I am having the table C and D. What is the first point? For the child table I have to write down all the possible non-trivial dependency. So now here we are having 3 attributes. So it can be like this, that AB determines C, BC determines A, CA determines B. Then there can be possibility A determines B, A determines C, B determines C, B determines A, C determines A, and C determines B. So like this there can be various possibilities. Right now we are considering these many possibilities for non-trivial dependency can be present in this child table. Here if you can see there can be only 2 possibilities, C determines D and D determines C. Okay, after that we have to see that these dependency hold true or not. So let's see. Now here AB determines C. If you can see in the main functional dependency it's directly present. So this possibility can be true. BC determines A. Now if I will take this dependency is not directly present in the question. If I will take closure also, closure of BC if I will take, then I will get BC, and BC is not able to determine anything in the question. Fine. So the closure of BC is BC only. So this is not true. This dependency will not hold true. Similarly, if I will take closure of CA, it will be CA only. Fine. Because CA together is not determining anything in the question. So this is also not true. Now this dependency A determines B. If you can see here, A alone is not determining anything. So here also this dependency will not hold true. B determines C and B determines A. If I will take closure of B, I will get B only, because in the question all these are not true. Now here, if I will take this one, C determines A. Now closure of C, if I will take, I will get C, and C determines D, and D determines A. Now here, but for this table we are only having 3 attributes A, B, C, so D we cannot consider, but we can say that C determines C and C determines A. So this dependency can hold true. Okay. Now we already took the closure of C, but B is not able to determine. So this dependency is also false. Okay. Now let's check here. If we will see here, C determines D is directly present, so I can tick it. Now D determines C is not directly present, but if I will take closure of D, what I will get? I will get D, then here I will get A, and that's it. Fine. That means D cannot determine C. Okay. So what are the possible functional dependencies? What I have to do? I have to take union of all possible functional dependencies. So here possible functional dependencies AB determines C, C determines A, and C determines D. These are the possible functional dependencies. Now what we have to do? We have to check with the original functional dependencies. What we have to do? We have to check with the original functional dependency. If both are equal, then we will say that this decomposition is dependency preserving. Now if you can see AB determines C, I can get directly, right? So this dependency holds true. Okay. Now next, C determines D. This is also directly present. So this is also preserved. Now D determines A. this is not directly present. So what I have to do, I have to take closure of D, determinants closure. Fine. And this time with respect to possible functional dependency I will do. So here if you see, D is not determining anything, so closure of D is only D. That means what? We are not able to preserve this functional dependency. So this is an example of lossless decomposition, but dependency is not preserved. Okay. Now here we are having one more example, and this example is from GATE question series. So here the question came like this, that a relation is given to you, functional dependencies is given to you, and decomposition of table is given to you, and then 4 options are there. Whether it's a dependency preserving and lossless join, lossless join but not dependency preserving, dependency preserving but not lossless join, and not dependency preserving and not lossless. And you have to tick the correct answer. So let's check. First we have to check for lossy or lossless. So 3 points I have told you to check that. First, see all the attributes are present or not. So if I will see AB and CD, this relation is having 4 attributes. Table 1 will give me AB, table 2 will give me CD. So if I will want to recreate the table, at least all attributes I will get. So that means first condition is satisfied. Second, there should be one common attribute between the 2 table. If you can see here I am having AB and here I am having CD, and the case is gone. It is a lossy decomposition. Fine. So if it is a lossy decomposition, that means because there is no common attribute. Fine. So dependency preserving and lossless, this point is gone. We cannot take A. Lossless join but not decomposition, not dependency preserving, this point is also gone. Now we are having 2 among C and D. There can be an option where it is dependency preserving but not lossless. It is not lossless, and not dependency preserving and not lossless. So these are the 2 options we have to tick. Okay. Now what we have to check, whether it is dependency preserving or not, and the answer will be in front of you. So what I have to do, I have to write down my tables like this, AB and CD. Here all the possible non-trivial dependencies I will write down. So if I will write down non-trivial dependency for this, here I can get AB, and here I can have BA. Here I can have C determines D and D determines C. Fine. Now I have to check whether these dependency, what possible dependency what I have written is true or not. How I will check? With respect to the dependencies given in the question. So if you can see, A determines B is directly present. So A determines B is directly present, I will tick it. Now B determines A is not directly given. So what I have to do? I have to take closure of B. If I will take closure of B, I will get B, and if you can see, there is nothing I can determine from B, so this will not hold true. Similarly, if you can see here, C determines D is directly present. After that I don't have to see anything, only 2 dependencies were there and both dependencies I got. That means what? This is a dependency preserving. That means my answer is what? My answer is C. But still, if you want to solve, we can solve further. D closure, if I will see, because D dependency is not directly given, if I will check the closure of D, I will get D, and that's it. I will not get anything. So this dependency is also wrong. And last point, what we have to do, we have to check the I have to take the union of these dependency, and I have to check with the dependency present in the question. And as you can see, A determine B and C determine B, C determines D is directly present. So the answer is dependency preserving but not lossless join. That's it for this session. Thank you very much.